Volatile oil characteristics. The initial producing gas oil ratio of the volatile oil is higher than the black oil reservoir. It's usually more than 2,000 and less than 3,300 standard cubic feet of gas per stock tank barrel of oil. So if the gas oil ratio is more than 2,000, then definitely I have, and less than 3,300, definitely I have the volatile oil. And I can also look at the stock tank oil gravity of the volatile oil. The volatile oil has a stock tank gravity of greater than 40. So if you remember, in the case of black oil reservoir, we set the API gravity of less than 45. So in volatile oil, we have API gravity of more than 40. So there is this 40 to 45 degree of API overlap between the black oil and volatile oil. So if I have an oil which has a black oil, if I have an oil which in the stock tank and the API gravity is like 42, then it could be black oil or volatile oil. In that condition, I'm going to look at the gas oil ratio. Okay. So if the gas oil ratio is more than 2000, then definitely that's a volatile oil. If it's less than 2000, then that can be classified as the black oil. Another property is, as I said, the light components. You have more of an intermediate, like C2 to C6 components in the case of volatile oil, which leads the phase envelope to shift toward the left in compared to the black oil reservoirs. And if I look at the formation volume factor, in this case, the formation volume factor is greater than 2. So initial oil formation volume factor is more than 2, which means you at the best condition, you can get half of the oil you have at the reservoir, okay? Because that's a reservoir barrel of oil over the stock tank barrel of oil. And this value is more than 2, okay? So basically, if you have 4 barrels of oil at the reservoir condition, you will get 2 barrels of oil at the standard condition. Why? Because at the reservoir condition, all these light components are dissolved inside the oil and the oil is swelled. When it comes to the surface, these light components starts coming out of the oil and oil shrinks. So those light components goes to the gas phase, and what you are getting is the heavier components. Okay, it's very similar to I always use this example like a can of Coke. Just pick a can of Coke, shake it, and then when you shake it, you increase the pressure basically inside, and then when you open it suddenly, what happens? Basically, you expose that to the reservoir, to that high pressure, to the atmospheric pressure. So most of this, light components with the gas goes out, and then basically when you pour it in a glass of in the cup or in the glass, then you will see a half full glass of Coke. However, if you open it slowly, basically you are managing the pressure. You don't let this to come to the surface at the to come to the atmospheric pressure at once, then you basically can have all of it. So that change in the pressure will lead some of the light components to go to the gas phase, and definitely you lose it. So you will not have it in the oil. And these kind of reservoirs, they have less than 20% of heptane plus. So the amount of heavy components is between 12 to 20%. So looking at the phase envelope, still they have a large phase envelope, okay? But in compared to the black oil, it's less. The reservoir condition is falling on the left side of the critical point. So if you remember, we said wherever your critical point is, if your initial reservoir pressure is less than your critical temperature of the envelope, or you are falling in the left side of the critical point, then you have liquid. If you fall on the right side, then you have gas. So this is still on the left side. So the reservoir temperature is less than critical temperature, exactly like black oil. But this time, the reservoir temperature is closer to the critical temperature. In the case of black oil reservoir, that reservoir temperature was far away from the critical point. Now it's closer to the critical point. Okay. The other property is this isovolume lines. These isovolume lines are not equally distributed, as we saw in the black oil. So if I have this graph and the previous phase envelope for the black oil, I can easily identify from the point that the volatile oil has a closer temperature to the critical point, and isovolumes are not basically evenly distributed. So if we are at point 1, basically we are at the unsaturated oil. So if we introduce gas, it starts dissolving gas in it, so it's going to be single phase liquid. And as we produce from this reservoir, the pressure drops at a constant temperature. It's still in the liquid phase till we hit the bubble point. When we hit the bubble point line, the first gas bubble comes out. So this bubble point line is actually 100% liquid. Theoretically, the first gas bubble comes out. And then if you drop the pressure more, we start losing, we start generating liquid where we start generating gas. So some more gas starts coming out of the oil. So here we have 90% oil, 80%, 70%, 60, and 50. So as we go below the bubble point, some gas bubble starts coming out of the oil. Okay. At what condition? At the reservoir condition. Okay. So if the pressure, if your operating pressure falls below the bubble point, you will start going to the two-phase. So you need to worry about the two-phase flow in the reservoir. And this is our separator condition, which basically is also in the two-phase. So basically at the surface, we also have the two-phase of gas and liquid. So these were two oil type of reservoir we had, the black oil and the volatile oil. The next type of reservoir we have is a retrograde gas reservoir, or what we call it gas condensate or condensate reservoir. In this case, the initial gas-oil ratio is more than 3,300, okay? So because the gas reservoir, the amount of gas we produce over the amount of oil we produce is much higher, okay? Initial gas-oil ratio generally is less than 5,000, okay, for this case, And as I said, if we produce at a pressure less than the dew point pressure, then we start losing liquid. And basically what it says, generally till that liquid doesn't reaches to 35% of saturation, they don't move. So, and that basically generates some damage. So you're losing some liquid at the reservoir and those liquids will not move. So you're losing it first and then you're also blocking the other, gas flow paths. So this is very critical to identify the retrograde gas reservoir and know how to operate it. The API gravity of retrograde gas is around 60 degree API, okay? So around 60 degree API, stocking oil, gravity, and also the gas-oil ratio more than 3,300 with the initial gas ratio, oil ratio of 5,000 indicates the retrograde gas reservoir. So now if you look at the phase envelope of the retrograde gas, so look at the critical points, more shifted toward the left. Now the envelope is shrinked, this is in compared to the volatile oil. The reservoir condition, the reservoir temperature is now higher than the critical point, okay? So we are in the right side of the critical point. So therefore we are in the gas reservoir. Remember in the case of oil, if this is my critical point, if I draw a straight line, in the left we have oil, in the right we have gas. So now that the initial reservoir condition is at the right side of the critical point, so we have a gas reservoir. So in the case of retrograde gas, the reservoir temperature should fall between the critical temperature and the maximum temperature of the envelope, okay? So if your reservoir temperature falls between critical temperature of the phase envelope and the maximum temperature of the envelope, so anywhere in between, then you have the retrograde gas reservoir. So it's a gas at point 1, and if you remember, we always said we are going to operate at a constant temperature. So as I operate it, the pressure will drop. So I'm still in the gas phase, the pressure drops until I hit the dew point. When I hit the dew point, the first droplets of liquid will appear, okay? And then if I continue producing from this reservoir, I'll go inside the two phase, so more liquid starts developing where at the reservoir condition. So it's not like the liquids are generating a single liquid phase at the first, but it's like you have a press media full of gas, and then you start dropping the pressure below the bubble point, below the dew point, and then you will see these liquid droplets appearing everywhere in the reservoir, okay? So they're not coming together generating the phase to be able to move. They are just droplets of liquid everywhere. So they start blocking the gas paths in your reservoir, okay? And since those saturations, the saturation of the liquid reaches to the point that the fluid can move based on the relative permeability, then you cannot produce that, okay? So this is very critical to make sure what type of reservoir fluid you have. If you have a retrograde gas, what is your dew point pressure? And make sure you always operate at a pressure above your dew point pressure. Because if you go below the dew point, you will lose all the volatile components and also you are start damaging your reservoir, okay? And as you can see, the separator condition is also falling inside the two phase. So basically you are producing some condensate at the reservoir, at the surface as well. Okay. So the next type of reservoir fluid is called wet gas. Okay, it's called wet because it produces gas, it produces some liquid at the surface. The wet gas reservoir phase envelope is basically much smaller than the retrograde gas phase envelope. Okay, so it's much smaller, and the reservoir temperature is higher than the Crichton term maximum temperature of the envelope. Again, this envelope is much smaller than the retrograde gas, so I know it's a very light component. The initial reservoir temperature is higher than the critical point. So if I draw the critical point, find the critical temperature and draw a line to the left, I have oil, to the right I have gas. So it's more, so it's a gas reservoir. The temperature is more than maximum temperature of the envelope, Crichton term. So it's not a retrograde. So it could be wet or dry gas. However, as I said, the wet gas produces liquid at the surface. So the separator condition is inside the two-phase. So you will produce some liquid at the surface. That's why we call it wet gas. So, but at the reservoir condition, no matter how you drop the pressure, you will never go to the two-phase. So you will never produce any liquid. So it's much easier to operate the wet gas reservoirs in compared to the dry gas, okay? In compared to the retrograde gas reservoirs. So it always stays gas phase, but when it comes to the surface at the separator condition, you will have some liquid. And then the last reservoir fluid is the type is dry gas reservoir. So in the case of dry gas reservoir, the envelope is much smaller. Again, if this is my critical point, I'm on the right-hand side, so it's a gas reservoir. The initial reservoir temperature is much higher than the maximum temperature of the envelope. And also the separator condition falls outside the envelope. So if this is the condition, initial condition, as I produce and drop the pressure, I'll always stay in the gas reservoir. And even if I bring that gas to the surface, the separator condition is also at the gas condition. So I'm not going to go through the two-phase. So this is a dry gas, will be gas, will produce gas, and I don't need to worry about producing liquid or dealing with the liquid in this reservoir. Okay. So we introduced 5 types of reservoir fluids. Black oil reservoirs with a much larger envelope, then volatile reservoirs, smaller envelope. In the case of black oil and the volatile oil, the reservoir temperature is less than critical temperature, so I'm to the left-hand side. The black oil has a uniformly distributed isovolumes. The volatile oil does not. And then the retrograde gas, where the initial reservoir temperature is between critical temperature and the maximum temperature of the envelope. And then I will produce liquid at the reservoir and at the surface, so it's very important to operate above the dew point. Then I had the wet gas reservoir, which the reservoir temperature was more than Crichton term, more than the maximum temperature of the envelope, but the separator condition was in the two-phase. And at last, I had the dry gas reservoir, which was gas and produced gas at all time. So in the next lecture, what we are going to do, we are going to study the behavior of the dry gas reservoir first, and then we go and we study the behavior of the liquid oil, and then having the two-phase.